Hello friends, today we will study the theoretical part on operations on divergent sequences. Before that, first we will take one example from exercise 2.7 on the operations on convergent sequences. So, see the example. Let S1 is greater than S2 greater than 0. S1 and S2 are two real numbers which are positive and S1 is greater than S2. And Sn plus 1 is defined as Sn minus 1 plus Sn upon 2 for every n greater equal 2. Okay. Then should add first S2n minus 1 is a decreasing sequence. Okay, is decreasing sequence. Second, S2n subsequence is increasing sequence. And third, Sn is convergent sequence. So here S1 greater than S2 greater than 0. Sn plus 1 is equal to Sn minus 1 plus Sn upon 2 for every n greater equal 2. Therefore, your S3 is equal to S1 plus S2 upon 2 belongs to S2 S3. S2 S3 and so it is the midpoint of S2 and S3 and length of, which implies your S2 is less than 0 less than S2 less than S3 less than S1 comma length of S2 minus S3 is equal to length of S1 minus S3. Length of S2 S3 and S3 S1 both lengths are is equal to length of S1 minus S2 upon 2 upon 2. Is it clear? Now S4 is equal to previous two terms sum, means S2 plus S3 by 2, which belongs to among S2 and S3, S2 is smaller than this, so S2 S3. Okay, which implies 0 less than S2 less than S4 less than S3 less than S1. Moreover, if you observe the length of S2 minus S4 is equal to length of S4 minus S3. This is equal to length of S1 minus S2 upon 2 square. That length will become half of that again, so it is 2 square. Okay. Continuing thus we get 0 less than S2 less than S4 less than S6. Okay, S2n and S2n minus 1 and so on S1 for every n. Will get sequence like this. Okay. Implies S2n minus 1 is decreasing sequence and bounded below by below by 0 or S2, while S2n is increasing bounded above sequence, increasing bounded above sequence by S1. Therefore, by Monotone convergence theorem, therefore, by monotone convergence theorem, monotone convergence theorem, every monotone increasing bounded above sequence is convergent, every monotone decreasing bounded below sequence is convergent. Theorem, S2n and S2n minus 1 are convergent sequences. So suppose limit n tends to infinity of S2n is equal to L, limit n tends to infinity of S2n minus 1 is equal to M, then S2n is less equal L, this L must be less equal M, this is 2n S2n minus 1 for every n, because S2n is increasing sequence. Okay. Since S2n is increasing sequence, implies limit of S2n is equal to L is equal to supremum of S2n. Okay, where n varies in n. And S2n minus 1 is decreasing. Implies limit of S2n minus 1 is equal to M is equal to infimum of S2n minus 1 where n varies in n. Is it clear? So if the given sequence is increasing, then it converges to, and it is bounded above, then it converges to its supremum, and this converges to its infimum. Okay, so we'll get this relation. Okay, so now to show L is equal to M. So for this mod of S2n minus S2n minus 1, this is equal to mod of S1 minus S2 upon 2 raised to n minus 1 for every n. For every n. And therefore, if I take limit of S2n minus 1, this become limit n tends to infinity of mod S1 minus S2 upon 2 raised to n minus 1. This is constant, it goes to 0, 1 upon 2 raised to n minus 1 goes to 0, and therefore this goes to mod of L minus M, and therefore L must be equal to M. Okay, therefore limit S2n is equal to limit of S2n minus 1. Now we know that if the sequence has subsequences S2n and S2n minus 1 converging to same limit, then that sequence must be convergent. Okay, this implies limit of Sn is equal to L exist, and therefore Sn is convergent sequence. Sn is convergence sequence. Okay. So last time we couldn't cover this example due to the time limit. So firstly I explained this one. Now we'll go to the operations on divergent sequences. So take the theorem. See the theorem now. If Sn and Tn are divergent sequences diverging to infinity. Okay. So let Sn and Tn be divergent sequences such that Sn tends to infinity, Tn tends to infinity as n tends to infinity. Then Sn plus Tn tends to infinity, Sn into Tn tends to infinity as n tends to infinity. So since Sn tends to infinity, Tn tends to infinity as n tends to infinity, therefore for m greater than 0, for given m greater than 0 and 1 greater than 0, there exist positive integers n1, n2 such that Sn is greater than m for every n greater equal n1 and Tn is greater than 1 for every n greater equal n2. Then Sn greater than m, Tn greater than 1 for every n greater equal n0 is equal to maximum of n1, n2. This implies mod of Sn plus Tn is greater than m plus 1 greater than m for every n greater equal n0 and Sn into Tn is greater than m into 1 is equal to m for every n greater equal n0. So what we proved, for given m greater than 0, there exists positive n0 such that Sn plus Tn is greater than m, Sn into Tn greater than m. Okay. Thus, for given m greater than 0, there exists positive integer n0 such that Sn plus Tn is greater than m for every n greater equal n0 and Sn Tn is also greater than 1 m for every n greater equal n0. Therefore, Sn plus Tn tends to infinity, Sn into Tn tends to infinity as n tends to infinity. So we'll take next result as, say theorem 2, if Sn and Tn are divergent sequences such that Sn goes to minus infinity, this goes to minus infinity, okay, then Sn plus Tn goes to minus infinity and Sn Tn goes to infinity as n tends to infinity. So as this goes to infinity, minus infinity, this goes to minus infinity, for given m greater than 0, Sn is less than minus m, Tn is less than minus 1. Is it clear? For n greater equal, then Sn is less than minus m, Tn is less than minus 1 for every n greater equal n0. Therefore, Sn plus Tn is less than minus m minus 1. This must be less than minus m. And Sn Tn is greater than minus m into Sn Tn. Sn is less than minus m. So, Sn into Tn is greater than minus m into minus 1. Because Sn less than minus m, Tn less than minus 1, so Sn into Tn become positive number. Sn into Tn become positive number. So their product the product must be greater than that. Must be greater than SNTN greater than m into 1 for every n greater equal n naught. And therefore, Sn plus Tn less than minus m, Sn into Tn is greater than m for every m greater equal n naught. So this goes to minus infinity and this goes to plus infinity. This goes to plus infinity. Okay. Now, if you take Sn is a sequence diverging to plus infinity, okay, and Tn is bounded sequence, theorem 3. The sequences such that Sn tends to infinity as n tends to infinity and Tn is convergent and hence bounded. Then so that then Sn plus Tn tends to infinity as n tends to infinity. This is theorem 3. So since Sn tends to infinity, or since Tn is convergent and hence bounded sequence, so remember, instead of convergent, even though there is boundedness condition only given, the result is true, bounded sequence. Therefore, there exists p greater than 0 such that mod of Tn less than p for every n. This is 1. Now since Sn goes to infinity as n tends to infinity, therefore for given m greater than 0, there exists positive integer n naught such that Sn is greater than m for every, or I'll take here Sn greater than m plus p for every n greater equal n naught 2. Now Sn plus Tn is greater equal Sn minus mod Tn. If Tn is positive, then mod Tn is Tn, and so Sn plus Tn is greater than Sn minus Tn. And if Tn is negative, then mod Tn is minus of Tn, so Sn minus Tn is Sn plus Tn, so we'll get equality there. So this is greater than, Sn is greater than m plus p, and mod Tn less equal p means minus mod Tn greater equal minus p for every n greater equal n naught from 1 and 2. This p get cancelled. Okay. Thus, for any m greater than 0, there exists positive integer m naught such that Sn plus Tn is greater than m for every n greater equal n naught. And therefore, Sn plus Tn tends to infinity as n tends to infinity. So take next as if Sn is sequence diverging to minus infinity and Tn is bounded sequence or convergent, then Sn plus Tn goes to minus infinity. So Sn goes to minus infinity, we'll get this to be minus m less than minus m minus p. Is it clear? Then Sm plus Tn. Now Sm plus Tn is less equal. Sm plus mod Tn is less equal Sm plus mod Tn. Right? Tn is always less equal mod Tn. So this is less equal minus m minus p plus p for every n greater equal n naught. Okay, from 1 to again, from 1 and 2. Right. Thus, for any m greater than 0, there exists positive integer n naught such that Sm plus Tn is less than minus m for every n greater equal n naught, and therefore Sm plus Tn tends to minus infinity as n tends to infinity. Okay. Now, if you take one sequence diverging to infinity, other diverging to minus infinity, then their sum may not goes to infinity, may not goes to minus infinity. That sequence may be divergent, may be convergent. Means if I take other type of combination, one sequence is divergent, other is convergent. Okay. One sequence diverging to plus infinity, other diverging to minus infinity. In that case, there is no any conclusion. There is no any conclusion. So try to construct counter examples related with that. So with this discussion, we'll stop today's session here. Thanks for listening lecture carefully. Bye bye.